Hello everybody. Having discussed the paradigm of divide and conquer, we now move over to the dynamic programming paradigm. In our overall methodology of conversion from recursive definition to a final solution, we have come across a very important aspect, and that aspect is identical subproblems in the recursive definition. And in order to handle identical subproblems, we used a technique called memoization. And this memoization, where we will solve identical subproblems only once and remember that solution, leads to the basics of the dynamic programming method, and that shall be the focus of our lectures in the next few sessions. We have discussed dynamic programming basics before, and among our discussions we found out that the basic tenets of dynamic programming include development of a recursive decomposition of the problem, and while in simple problems like the Fibonacci, the recursive decomposition is just a simple decomposition. In many other cases, it may involve optimization across possibilities, and therefore there is always this concept of an optimal substructure. And this optimal substructure is at the heart of dynamic programming, where we solve these optimal substructures first before we solve the larger structure. The second aspect, which is the core aspect of dynamic programming, is handling identical subproblems. And we have seen before, these identical subproblems cause an enormous difficulty to us in terms of the complexity of the problem. So we need to ensure that we solve identical subproblems and we store their solutions, and the storing of the solutions is called memoization. So memoization and reuse is at the heart of dynamic programming. After that comes the evaluation function. How do I evaluate this recursion? And we have seen that we can evaluate it either in a top-down manner, which is going with the recursive definition but with memoization, and in many cases we can do an iterative bottom-up solution to the problem. Finally, we will have to create the data structures to reach our solution. A large number of problems fall under the category of dynamic programming. We have seen the Fibonacci type, or in our words, the Pingala type of recursions. We will see in today's lecture the matrix chain multiplication problem, which is a classical problem. This matrix chain multiplication is a classical problem which we shall see. And then there are several other problems which are string related problems. Given two strings, how do we find certain commonalities between these strings? And this leads to several problems like the longest subsequence, longest common subsequence, It also leads to other problems like the sequence alignment in biology, the gene sequence alignment. It leads to a number of NLP, natural language processing related problems of word matching, spelling corrections, etc., etc. There are several other matrix operations like the transitive closure of the matrix. There are graph algorithms which are related to shortest paths, etc. Then there are problems like the coins problem that we saw, whose more popular variation is called the knapsack problem. And in terms of data structures, there are problems like the optimal binary search trees, which lead to dynamic programming solutions. We just quickly revise our Fibonacci problem. Our Fibonacci series was Fn is equal to Fn minus 1 plus Fn minus 2 for n greater than equal to 2, and it was 0 for n equal to 0 and 1 for n equal to 1. And this is how we defined our Fibonacci series. And we realized when we did this Fibonacci series, we saw examples where if we try Fibonacci 5, we have to do Fibonacci 4 and Fibonacci 3. And for 4 again we have to do 3 and 2. For 3 we have to do 2 and 1. And then again for 3 we have to do 2 and 1, and so on and so forth, and leads to identical subproblems. And to solve for such identical subproblems, we decided to keep an array F, and we had the done array which indicated whether the value was already computed or not, and we designed all this in more details, and we have done this before, where we set done 0 equal to done 1 equal to 1, all other done I equal to 0. We set F0 equal to 0, F1 equal to 1, and then we wrote the evaluation function where we wrote our eval Fn, and the first thing we checked is if done n, return Fn. Here done n means done n equal to 1. If done n equal to 1, return Fn. If that is not the case, then obviously what we do is we compute z m equal to eval f n minus 1 plus eval f n minus 2, and then we set done n equal to 1. Then we calculate Fn equal to m, and we return Fn. This way we compute each of these items only one by using the done array. We also know that we can compute it bottom up like this, from I equal to 0 to I equal to n, and we can get a simple iterative algorithm where after having done the initialization steps, so we have done f0 equal to 0, f1 equal to 1, and then for I equal to 2 to n, do fi is equal to fi minus 1 plus fi minus 2, and that computes all our computation. We also know that we don't need to, we need only two variables, only two additional variables are needed, and if this recursion instead of f n minus 2 is some n minus k, then we know that we need more base conditions, and I leave it to you to work out what this generic algorithm will be. We also saw a more generic evaluation function of these recurrence relations, where the fn is equal to some rn if cn is true, and is equal to f of gn plus f of hn if cn is false, and we know that where cn, rn, gn, hn are not recursive in some and can be computed deterministically, let us assume this, and then in order to do this, what we decided in our previous class was we have this F array, and then we have this done I, and we had three values for done I, because here we don't know whether there is a dependency, the values of f of gn and f of hn, because gn and hn can be anything. For us, it is difficult to get an iterative algorithm, and in a recursive algorithm, there is a problem of cycles. So we decided it is 0 if fi is not, if it has not been evaluated. It is 1 if evaluation has begun but not completed, and 2 if the final value is computed. And we have seen in our discussion that the algorithm eval fn first checks if done n equal to 2, return fn, then checks the base condition, that is if cn equal to true, then it begins the evaluation of the function. So it makes done n equal to 2, fn equal to rn, and it returns fn. The most complicated part comes if done n is 1. This means that it is neither a base condition nor it has been completed. So it has entered, but done n was not 2, so it has not been completed, and therefore here is a return cycle detection. That means we have gone into a cyclic loop, and if that is not the case, then you begin your evaluation steps. You set done n equal to 2, done n equal to 1, because you are now starting the computation, because that means that till now it is not 2, it is not a base condition, it is not 1, so done n is 0. This is what done n is initialized to at the beginning for everybody. Then we compute x is equal to gn, we compute y is equal to hn, and then we evaluate z is equal to eval f x plus eval f y. Then we set f of n equal to z. Then we set done n equal to 2, and we return f of n. This way we also detect cycles, and if required we could also memorize the values of Rn, Fn, Gn, Hn, Cn and everything else. But this is how we have discussed how to evaluate this problem. We now come to our first problem, which is the matrix chain multiplication problem. The matrix chain multiplication problem is stated as follows: that we have a series of n matrices M1, M2, Mn to be multiplied. Now matrix chain multiplication in this form is associative but not commutative. So as you can see, we could multiply it this way, or this way, or this way, or this way. And we shall see that the order in which we multiply it is the complexity of the number of multiplications to be done varies. We know that if A is a P by Q matrix and B is a Q by R matrix, then AB requires P into Q into R multiplications, because every row of A must be multiplied by a column of B to give the ij location. So for every ij location you need order of n, order of Q multiplications. So it is P into Q, that is the resultant size, P into R, which is the resultant size, and for every one you require Q such multiplications, because Q is the common element. Now if M1 is a 10 by 30 matrix, M2 is a 30 by 5 and M3 is a 5 by 60 matrix, then if we do M1, M2, M3 as M1, M2 first, followed by the result of this, so let this be P, then for computing P we require M1 into M2, which will require 10 into 30 into 5. So because this is 10, this is 30 and this is 5, it will require so many, and this must be multiplied with M3. And in order to do that, because M3 itself is a 5 by 60 matrix and M1 into M2 will become a 10 by 5 matrix, so it will require an additional of 10 into 50 into 60. So the total will be this plus this, which is 4500. On the other hand, if you do this first and then this, then to compute this you require so many multiplications, and to compute the second part you require so many multiplications, and this becomes a total of 2700. And as you can see that the order matters significantly. So now the question is, how do we find out what is the optimal sequence for us to multiply these, decide on the optimal sequence for multiplying these matrices. This determination of the optimal sequence and the minimum number of multiplications is the matrix chain multiplication problem. So in the matrix chain multiplication problem, you are given matrices M1, M2, M3 right up to Mn. Each Mi has got a M1 has got a dimension P0, P1, M2 has got P1, P2, M3 has got dimension P2, P3, and Mn has got dimensions Pn minus 1, Pn. Now I have to determine what is the total number of multiplications, what is the optimal sequence. So for that we set up our first thing in dynamic programming is to set up the dynamic programming equation. Again, as per our methodology, we set up this recursive equation. And the recursive equation is as follows. Mij, let Mij be the optimal multiplications for multiplying Mi to Mi plus 1 to Mj. Then the recursive equation is Mij is equal to 0 if I is equal to j, because if it is M11, M1, M22, etc., etc. Otherwise, you have to look at all the options, that is Mik plus Mk plus 1 j. That means I will break it up into Mi1, Mik and Mk plus 1 j. That means I will break this up into Mi to k and then Mk plus 1 to j. So I'll break it up into two parts, part 1 and part 2, and I will break it up into as many ways and I can do part 1, part 2. And if I break it up into like this, which is Mik and Mk plus 1 j, I break it up into this form, then when I compose these two, I will require Pi minus 1 into Pk into Pj multiplications after this. And I want to do this over all k and want to find the minimum from k equal to I to j minus 1. So this is the condition if I is less than j. So this gives me my dynamic programming equation, which is my optimal substructure equation. And suppose, as in our case, where we have our matrices, we have our M1 is a 10 by 30, M2 is a 30 by 5, M3 is a 5 by 60, and M4 is a 60 by 4 matrix. Then for me P0 is 10, P1 is 30, P2 is 5, P3 is 60, and P4 is 4. Now for this I need to find the optimal sequence, and we have to analyze how do we obtain this optimal sequence. In order to do this, let us look at the recursive structure. So this is the recursive structure. That is M1, we have our problem of M1 to M4, and in order to understand this a little better, let us rewrite our Mij is equal to 0 if I equal to j, and is equal to minimum for k equal to k equal to I to j minus 1, Mik plus Mk plus 1 j plus Pi minus 1 into Pk into Pj if I less than j. So this is my recursive definition, and as you can see, when we open it up, we have got two kinds of computation. One kind we have marked by these black nodes, which are either a base condition or like a base condition, and the other or a min node. For example, this M1 to 4, M14 can be done by M11, M24, or M12, M34, or M13, M44. Now we have to take a minimum of all these. So these nodes are min nodes, or these nodes are base nodes. So all the dark nodes are min nodes or base nodes. I have shown these also as base nodes because M12 will be done as M11 plus M22 plus P0 into P2, P1 into P2, which is the same as, because M11 into M22 is are both zeros, so that is why I have left it like this, because this is also like a base node. The others are what are called recursive nodes. The red ones are all recursive nodes. And as you can see that this M34 comes from this side as well as from this side. M23 comes from this side as well as from this side. M12 is here as well as here. So nodes are duplicated. So how do we compute this? We will have to compute this by recursion. And in order to compute this by recursion, we will have to compute it by our two steps. One is our top-down algorithm, the other is our bottom-up algorithm. And in order to compute it with the top-down algorithm, we will have to memorize, and we will have to memorize all our values. And if that value is computed, we will just retrieve that value. So we again go back to our methodology of development of our top-down algorithm. So for our top-down algorithm, we keep an array Mij, and we keep a value done ij. And we use that in order to determine. So we initialize done ij to 0, and Mij is also initialized to whatever values it has. Now how do we compute? We just write down our eval function, eval m I comma j. We check if our approach is identical to as before. If done ij equal to 1, return Mij. Otherwise, if I is equal to j, then we set done ij equal to 1, we set Mij equal to 0, and we return Mij. We could have done this as an initialization as well and done it before. Otherwise, if this is not the case, now is our recursive condition, where as per our definition here, we have to compute the minimum of all combinations of Mik and Mk plus 1j and the additional multiplication term that we require for all k equal to I to j minus 1. So, in order to do that, we will have to set a tentative value to infinity, and then we will do a for k equal to I to j minus 1 Vk is the recursive evaluation eval m I k plus eval m k plus 1 j plus pi minus 1 into pk into pj. And once we have done this, we are assuming that the p values or the dimension values are stored, and then if this is done, all we now need to do is if Vk is less than val equal to Vk. And once we come out of the for loop, we decide done Ij equal to 1 and M Ij equal to val, and we return Mij. And we can see that this method will reuse the values and compute every Mij exactly once. Because it computes every Mij exactly once, there are order n squared Mij values for an matrix of this size, n such matrices. For n such matrices, we have an n by n Mij array, and for each such work we have to do an internal for loop of k, so that will be at most order n, so the total complexity of the algorithm will be order n cubed. And if you go back here, you can see that this order n cubed algorithm will be executed in a depth first manner. At the min nodes, the min value will be computed, and at the recursive nodes, the recursive value will be computed. And if we want to just have a quick see as to how this happens, from M14, let us take this node. For this M14, we will first go to this side. From this side, we know M11, this value, we know this value, so let us use a different color. So M11 we know is 0. Then we come to M24. So once we come to M24, this can be done in two ways. So let us go this side. Once we go this side, we know that this value M22 is 0. Then we come to this value M34. M34 is almost a base condition because it is two direct multiplications, and M34 here, given M2 is a 30 by M3 is a 5 by 60 matrix, and M4 is a 60 by 4 matrix. So this computation will be 5 into 60 into 4 of 1200. this will estimate to 1200 operations. Now it will come back, once this is done, it will come back and compute the value here. So this value returns 0, this value returns 1200. So the value here that is computed is 1200 plus the additional as per the recursive equation of the pi minus 1 pk pj, and that will turn out to be 30 into 5 into 4, which is 1800. So from this side 1800 will go. But this is a min node, and this requires to now compute this side. When you go to compute this side, you will have to compute M23, which is this node. And M23 is a direct node, direct multiplication, which will lead to a 30 into 5 into 60, which is 9000 multiplications. This is what this will lead. And this goes to M44, which is 0. Therefore, this one will be 9000 plus M24 based on this equation of our pi minus 1 pk pj will require a 30 into 60 into 4, which will yield a 16,200. So from this side we get 16,200, and this being a min node will produce this side, and therefore this will be 1800. Now once this side is 1800, then this computation is 0 plus 1800 plus this computation M11 into M24, M1M1 and M2M4, which will basically be a multiplication of 10 into 60 into 4, which will yield 4200, and from this side 4200 will come. Then it will go into this recursion, and when it goes to this recursion, it will compute M1 M2, and M1 M2 value that will be computed will become a direct computation of 10 into 3, 30 into 5, which is 1500, and M3 M4 we have already computed as 1200. So from this side 1200 will come, from this side 1500 will come, and the computation here will be 1500. The computation here will be 1500 into plus 1500 plus 1200 plus this additional pi minus 1 pk pj, which is 10 into 5 into 4, and this will yield 2900, and from this side 2900 will come, and then we have to go this side, and once we go this side we will again find out what is the value of M1 M3. M1 M3 will come from M2 M3, which is already computed, so it will not compute it again, plus it will utilize M1 M1 plus M2 M3. M1 M1 is 0, and it is not difficult to see, as we have done just in the previous page here, of those values. We will get back 27,000 here, so we will get M1 M2 as 27,000, and we will get this as 4,500. Both these computations we have seen here, 4,500 and 27,000. These will come from this side, and M1 M2 will also not be done again because it has already been done before. And once we get these two values, therefore the value here will be the minimum of these two, and the minimum of these two is 4,500, because this black node is a min node. Now we can compute this value, which is 4,500 plus because this side is 0, it will come an additional 10 into 60 into 4 will come. 10 into 60 into 4, and this will lead to a 6,900 step. So from here we will get 6,900, and out of these three, the final result which we will get is 2,900. And once we know that the final result is 2,900, the actual path is this one. This one has got these two sub-problems, and therefore we know that the optimal multiplication sequence is this combination, and this combination means this combination. So this is how the top-down algorithm will work, and the top-down algorithm will compute every step only once, and therefore will compute it in order n cubed time. If we look at this top-down algorithm more carefully, and we look at the structure of the whole matrix chain multiplication, we will be able to see that an iterative algorithm is not difficult to obtain. If we create the n by n Mij structure, which is 1, 2, 3, 4, 1, 2, 3, 4. If we create this structure, then we can see that these will all be zeros. And therefore, after computing these, we will compute this in the second step. Then we will compute this in the third step, and we will compute this in the final step. And this M14 will give me my optimal solution. So in order to get my M14 optimal solution, I now have to develop an iterative algorithm. So in order to develop this iterative algorithm, we will go by difference. Initially a difference of 0, then a difference of 1, which is this row, then a difference of 2, then a difference of 3, and so on and so forth. So just to do that, we will develop our algorithm. First we will do our initialization, and in our initialization step we will write as follows. For I equal to 1 to n, we will set m I equal to 0. Now we will do the iteration, and we will start with differences. So our difference will initially be 1, 2, 3, 4, and so on. So now we will say let our difference variable be diff equal to 1 to n minus 1. Our difference value will be 1 to n minus 1. So for our difference value of 1 to n minus 1, that means f1 2, 2 3, 3 4, and then 1 3, 2 4, and then 1 4. So difference will start varying that way. Then we will write our I and j. Therefore for I equal to 1 to n minus diff now we will create j. J is equal to I plus diff. Then now we will do a loop for varying k, and therefore again like the val, we will initialize mij equal to infinity, and for k equal to I to j minus 1 as per our recursive equation, we will now compute q is equal to m. Now we don't need to call recursively because we know exactly a pre-computed value exists, plus p I minus 1 into pk into pj, and we check if q is less than mij, we set mij equal to q, and that ends my for statement here. This ends this for statement, and therefore this whole thing algorithm, which was my iterative eval, which started here, will now end here. And if we create our previously known p-values as per our past definition, where we have got P0, P1, P2, P3, P0, P1, P2, P3, P4, and we know these values are 10, 30, 5, 60 and 4, then we can create this array, and by creating this array we can simply assign the values 1, 2, 3, 4 for this array, and this is 1, 2, 3, 4. So these parts of the array are not used. So this is how we compute. We initialize in the first round, set all this to 0. Then when diff is 1, we compute M12, and M12 is computed based on this formula, 10 M0 into 1 into 2, so it will yield 1500. Similarly, this will yield 9000. Similarly, this will yield 1200. Once we have these, now I am ready to compute M13, which will come from the minimum of these two sides plus the additional computation. This will come to this will come to 1800 like we saw, and this will come to 2900. And this is how you compute it. So every row of this order n squared elements of the Mij matrix will be now be n squared elements will be now done in this loop order n times. So we will get an order n cubed algorithm. So here again we have got an iterative algorithm because we know exactly how to do. But as I have discussed earlier, always the iterative algorithm may not be possible, and in that case the generalized top-down algorithm, though it appears to be more complex with a done array and things like that, but it also does an order n cubed computation. So to summarize, we have again seen the tenets of dynamic programming, in which there is a recursive substructure which needs to be evaluated by memoization and reuse, and we can get both top-down and iterative. And this top-down is a recursive algorithm, and iterative algorithms. In this particular matrix multiplication, we could not save any more on the memory, but you can still have a look whether you can use fewer memory elements. What is the minimum number of memory elements you can use? Because once you have computed every diagonal, you don't need those anymore. You can release them, but you can make out that you will at least require a certain number of order n squared elements in any case. With this, we come to the conclusion of this first lecture on dynamic programming paradigm, though we have done other problems before. In subsequent lectures, we shall go through more details and more examples of the dynamic programming.